Today we will tell us about the Kikuchi.
Thanks, Ron. That's okay. Okay. I was worried that's on my computer. That would be a little bit harder to resolve. Okay, yeah, thank you all for coming to the talk. Sorry. Kikuchi matrix. I'll say a little bit about why it's Kikuchi matrix in a bit. Yes, so I'm actually going to tell you a little bit about this unpronounceable class of matrices and why they're interesting. And I should say that this is based on joint works with some amazing people. So Omar and Siddhant are PhD students at Berkeley. Tim and Peter are PhD students at CMU, and Venkat, my colleague. So, you know, I have the word method in the title. I'm using it in the weak sense that, you know, Polya would have been okay with. So Polya said that, you know, if you have a trick that can prove one theorem, well, it's a trick. But if you can prove two with it, then it's a method. And that's the weak bar I'm setting for myself for calling this, you know, the Kikuchi matrix a method here. Okay. So, you know, I'm going to tell you a lot more about this, but at a very high level, the Kikuchi matrix method is a way to think about some girth problems in hypergraphs. So girth means, you know, length of the smallest cycle. And, you know, in some sense, this is a method that allows you to reduce these hypergraph problems, which are often hard to reason about because perhaps we are not as good at hypergraphs as we are at graphs. And then somehow, you know, reduce them to these carefully constructed graphs out of them and somehow reason about them there instead. So, you know, a little bit about the name and why, you know, I'm using it. So Ryoichi Kikuchi was a physicist, and I don't think he ever cared about hypergraphs or CSPs, at least not in the sense that I care about them. He actually thought about statistical physics, and in the context of statistical physics, there's a notion of free energy. Again, none of this is relevant to the talk. I'm just trying to explain the nomenclature. So, you know, if you heard of beta free energy, then there is an analog of beta free energy called Kikuchi free energy. And it turns out that this notion of free energy inspired an algorithm for a continuous statistical inference problem called Gaussian tensor PCA in this beautiful paper of Alex Vine, Ahmed Alaoui, and Chris Moore. And they are the first ones who observed that, you know, if you somehow compute this Kikuchi free energy for some quantities arising in, you know, these Gaussian tensor PCA, then the Hessian of this free energy has the kind of structure that I'm going to talk about today. None of this is relevant because I'm going to just tell you the matrix and it's going to be digestible in a minute. So I'm just trying to explain to you why I'm using the word Kikuchi. So that's the origin of the word. Okay. All right. So I told you it's a method. So what can it actually prove? So I'm going to tell you in this talk, actually most of this talk is about the first 2 bullet points. I realize that I won't probably have time to do anything more. But, you know, I'll tell you about, you know, a hypergraph Moore bound, so a certain girth problem in hypergraphs, and how actually you can resolve it using this Kikuchi graphs. I'll tell you a algorithmic problem about random and in fact semi-random constraint satisfaction problems. So like, you know, certain random models of K-SAT, for example, and you know, how to solve them again using the same method. Very recently, you know, we were able to actually also get some lower bounds for locally decodable codes using the same method. I likely won't have time to tell you about how this works. I'll try to hint at it at the end. And of course, I can tell you more offline. And actually, I should say, you know, when I was trying to, for the first time, trying to make slides for this talk, it was like 4 or 5 days ago, a new paper appeared on Archive by Castro, Silva, and Briet, who actually used this method for yet another application. So, you know, they study the problem of similarities theorem with random common differences. And they show that actually you can get an improved bound by, again, you know, using the same Kikuchi matrix method. Another very recent application of the same method. So, you know, this is upcoming work, but, you know, I'm going to talk about what is called as a refutation problem, but there is a related problem of solving, you know, certain smooth instances of planted CSPs. And we can show that, in fact, the same method is useful even for that problem. Okay, so none of this recent stuff is going to make to my talk. I'm just going to tell you like the initial method, the main idea, and My goal is to somehow, just tell you about this construction of the matrix and how to reason about it, because my hope is that you'll be able to use it in other applications. Good. So let's start by, thinking about this hypergraph Moore-bound problem. Okay. The reason I'm starting with this, by the way, is like, it's a clean problem that hopefully you'll appreciate in like less than 1 minute. You may not buy the motivations for studying it, but hopefully you'll enjoy thinking about it. So, Moore bounds are, basically statements that say that if you have a certain number of edges, then you must have a cycle of some length. So they're like trade-offs between the length of the smallest cycle in graphs and hypergraphs, and how many edges it has. So let's start with this classical question that in some sense is the 0th question one could ask in this direction. Suppose I give you a graph on n vertices, okay? And suppose I promise you that it has n times d over 2 edges. So its average degree is d. The question is, how large can you make the girth of such a graph? Now, if you think about it, if d is 2, that means that I have a graph on n vertices and n edges. If you wanted to maximize the girth, you should simply choose one giant cycle, right? So in this case, the length of the smallest cycle is n. So the question is, what happens if d is a little bit larger than 2? Let's say d is 3 to begin with. Does anyone want to take a guess what the length of the smallest cycle would be? Yeah, it's quite funny that Noga is taking the guess, because I'm actually going to quote a theorem of Noga. So this was actually a conjecture of Bolobash from 1978, and Noga, along with Alon-Hoory and Linial, basically proved it. They showed, in fact, that if you have a graph with average degree d, then it must have a cycle of length at most 2 times log of n to the base d minus 1 plus 2. Now, this might look a funny bound, but here's how to think about it. Think about the special case of a d-regular graph, okay? And think about trying to construct a d-regular graph while avoiding a cycle as much as you can. So think about like starting from a vertex. You have like d neighbors, they all must be distinct. Then you take their neighbors, and the branching factor is d minus 1, and they must all be distinct. And if you go on doing this, well, in like, log of n to the d minus 1, base d minus 1 steps, you'll basically run out of vertices. And then, if you just join 2 leaves and just basically get a cycle, that's the length of the cycle you'll get. And what the AHL theorem says is that basically this is essentially the best bound, or at least the bound that holds for all graphs, regardless of whether they are, regular or not. So that's why it's called the irregular Moore bound. Now, this is again not a major concern for us, but the factor 2 in front of this is actually a cause for quite a bit of research. We should ask, for example, can we construct high girth graphs? Can we construct graphs of average degree d that actually match this bound, for example? We don't know that. The best examples we have are basically, certain expander graphs that achieve a 4/3 instead of 2 bound there. And the question of whether you can actually make that 4/3 go to 2 is actually an open question. Lots and lots of work actually. Anyway, so that's not my concern. I'm going to think about hypergraphs instead. I want a theorem like this. I want to think about a question like this for hypergraphs. Okay. So for example, let's say you have a 3 uniform, or more generally k uniform hypergraph. I want to ask the same question. What is the minimum number of edges it has to have so that it has a length, cycle of some given length? Okay. Actually, before I do that, I need to tell you what does it mean to be a hypergraph cycle. There are actually multiple notions of it, and I'm in fact using this word somewhat non-standardly today. But permit me this leeway because I want to connect it to AHL. So here is like a property of cycles in graphs that you all agree with, hopefully. A cycle is a subgraph such that every vertex has even degree in it. In fact, it's exactly 2. In fact, if I were to define, we lived in an alternate universe where I defined a cycle as, a subgraph, which has even degree for every vertex, it will either be a cycle or a union of cycles. And in particular, if I were to define girth as basically a subgraph that has this property of the smallest number of vertices, you would still get the usual notion of girth. So this, is a reasonable notion in the sense that it matches the notion of cycles and girth in graphs that you care about. Okay. Now I should say that I've dropped the connectivity requirement. So in some sense, I've dropped some combinatorial properties of cycles when doing this. Hopefully, you're still okay with this definition, because I can actually generalize it to hypergraphs. So a cycle in a hypergraph is simply a sub-hypergraph, meaning just a collection of hyper edges, such that every vertex has even degree in it. Okay. So exact same definition, except now my edges are 3 uniform and k uniform in general. Okay, good. So you might ask, why should we care about this? It's a rather awkward notion, but actually, there is one. I'm giving you maybe one more motivation in the middle of the talk, but one motivation that's easy to explain right away is that this notion of cycle actually captures some coding theoretic properties that you might be interested in. Okay, so for example, if you think of, let's think of graphs. If you think of graph as describing to you linear equations, so for example, each edge ij, think of them as corresponding to equations xi plus xj is 0 or 1 modulo 2. So think of like, a graph as describing two sparse linear equations for 2. Then a cycle is simply a linear dependency in such a system of equations. And in particular, the smallest cycle is the smallest collection of equations that happen to be linearly dependent. It turns out that such properties have meaningful relations to concepts in coding theory. They correspond to distance of a code, and that's why you care about them. Now, a hypergraph in the same sense corresponds to 3 sparse linear equations instead of 2 sparse linear equations. So, in some sense, this notion generalizes naturally and corresponds to distance of a code. And so that's why, this extremal trade-off between number of hyperedges and the girth is equivalent to just proving rate versus distance trade-offs. And this sparsity condition that I have on the equations, if you interpret it coding theoretically, it corresponds to, some column sparse LDPC codes. Anyway, none of this is like super important, but I hopefully, I'm trying to convince you that this is not such a boring quantity to look at. Okay, good. So let's reason about, when does a hypergraph need to have a small cycle? Okay. Now, because of this linear algebraic connection, I hope you'll all agree that if I have a hypergraph on n vertices and it has at least n plus 1 hyperedges, it's got to have some cycle, and its length would be at most n, right? Just because any set of n plus 1 equations is linearly dependent, right? So we have one endpoint of the trade-off. You can ask, just like the graph case, what is the minimum number of hyperedges that a hypergraph on n vertices must have so that it has a logarithmic length cycle? Just like in the context of graphs, we know that it's just basically more than n edges, or more than, like, let's say 1.1 n edges. We can ask, what's the similar threshold for hypergraphs? So this question was studied back in early 2000s. So there's a theorem of Asaf Naor and Jacques Verstraete, and later on an improvement due to Feige. They basically showed that if you have a k uniform hypergraph with n to the k over 2 hyperedges, then it must have a log n length cycle. And now I'm agnostic about polylogarithmic factors inside the statement. In fact, Uri's result makes it just a log n, so it's not too bad, but it's not a constant. Okay. Now here's how to think about it. If k is 2, then a 2 uniform hypergraph is simply a graph, and n to the k over 2 happens to be n. And if you're agnostic about log factors, then basically this is a very fudgy version of the AHL theorem. What this is saying is that for hypergraphs, the threshold really becomes n to the k over 2, where a log n length cycle arises. Okay, so now we have 2 points on this trade-off. We know that if you have about n or n plus 1 hyperedges, then there's got to be a length n cycle. If you have n to the k over 2 or more hyperedges, there's got to be log n length cycle. And you can ask what happens in between. So maybe you would guess, for example, that there is a sharp transition, or you could guess that there is a smooth interpolation. And such a guess was in fact made by Feige. So Feige basically conjectured that there is a smooth interpolation, so to speak, between these 2 extreme points. So what he did, he parameterized this line I showed you before by a parameter L. So this looks like a mouthful, but it's actually not. Let me explain why. So think of like 3 uniform hypergraphs. Okay. So if you have n to the 1.5, so that's n times root of n over root of L, is an expression that basically goes from n to the 1.5 when L is 1 to n when L is n. So as this parameter L increases from 1 to n, the density drops from n to the 1.5 to n. So it's basically a parameterization of this line between n to the k over 2 and n that I showed you on the previous slide. So this L is a parameter that basically tells you where you are in between. Okay. And what Feige is saying is that if you are at a point parameterized by L, then you must have a L log n length cycle. And this is interesting because this conjecture is positing that there is a regime where there is an n to the epsilon length cycle and a root n length cycle and so on. There is no such, in some sense, there is no such interesting regime for graphs. But for hypergraphs, we are saying, oh, there are like interesting density regimes where cycles of length n to the epsilon, etc., exist. Okay. So what was the motivation of Feige? Well, Feige was able to verify this bounds, which are like not so hard to verify, by just some probabilistic method and second moment method for random hypergraphs. So conjecture is basically saying that random hypergraphs are extremal, at least in some fudgy logarithmic factor kind of sense. Good. So what do we know about this conjecture? Well, it's true for random hypergraphs. There is some work in this direction. So there's a paper of Noga and Feige. There's a little lemma actually in the paper of Noga and Feige that actually gets a trade-off, a non-trivial trade-off for the case of 3 uniform hypergraphs. So we actually wanted a L log n cycle to exist when the density is n to the 1.5 over root L. So the theorem that they prove gets you n square over L versus L log n trade-off. So it's off by like maybe root of n over L factor. And in general, there was a new approach based on some combinatorics of some generalized girth problems that Feige and Tal Wagner initiated in Tal Wagner's master's thesis. That's really all essential work I know about this problem. And what we did in this very first paper that we use the Kikuchi matrices in is basically prove this conjecture up to a polylogarithmic factor extra slack in the number of hyperedges required. So we proved that if you have a hypergraph with that many hyperedges at the top, n times n over L to the k over 2 minus 1, plus an extra log to the 2k and strapped in, then in fact you have a L log n length cycle. More recently, we were actually able to get a slightly simpler and tighter argument. And we were able to prove that in fact, the same conjecture is true up to a single logarithmic factor slack. So, this last log n is like kind of nasty. I have some, conjectured approaches that could potentially remove it, but yeah, we haven't been able to do that. By the way, usually I'm not someone who frets about log factors, but here it seems kind of important. It seems like a very basic question, so we should probably know the right answer. One thing I'm very excited about is that we get, what looks like a very different proof of the result of Noga and Hoory and Linial about graphs, in this way. So, we get a new spectral proof, which actually matches, exactly the same bound, this 2 log n to the base d minus 1 plus 2. We get the exact same bound via a new argument. So we of course don't improve that bound, and I don't think it can be improved, but we get a new proof, which is kind of nice to have a technique that somehow generalizes. Yes. Yeah, for graphs, I think we use some specialized machine using like this Ihara-Bas formula that allows us to basically get the right constant. For hypergraphs, in some sense, we don't have that tight a control of the spectral bound that we are looking for. I guess I'll try to tell you a little bit more detail. Any other questions so far? Okay, so then I can just tell you how the proof works, and I'll try to tell you what this Kikuchi matrix and how it appears in this proof. So let's try to prove this basic result. Okay, we'll try to argue that every 4 uniform hypergraph with n square over L hyperedges has L log n length cycle. Okay, now I write it as 2R because the approach I'm going to use always in some sense recovers an even length cycle. That's reasonable in this kind of linear algebraic context. And I should say that this trade-off is basically the specialization of Feige's conjecture to just case of k equals 4. So if you plug in L equals 1, you get n squared, which is n to the k over 2 when k is 4. Okay, good. And why am I using 4 and not 3? Well, it turns out that even numbers are much easier here than odd numbers. So I'm using the the least even number bigger than 2 to illustrate the idea. Okay, so the 4 is special because it's the least even number bigger than 2, as you all know. Good. So let's introduce this graph, because I told you that the way to prove this theorem is to reduce it to like some calculations on a graph. So here is the Kikuchi graph built from the hypergraph we were given as input. The Kikuchi graph is in fact a parameterized family of graphs, one for each possible value of this parameter L. Okay, now I'm doing something shady here. L is indexing both the number of hyperedges I have and the Kikuchi graph that I'm going to use. At first, I thought maybe I should not do it, but I decided to do it because in the end, this is in fact the right setting of parameters. So I kind of want to drive that home. So I'm going to continue to use this abuse of notation where I use the same parameter to index the Kikuchi graph and the number of hyperedges. Okay, so but in principle, they could have been different. So the Kikuchi graph at parameter L, the vertices of this graph are simply all possible subsets of size L of the vertex set of the hypergraph. Okay, so I have in particular n choose L different vertices, and a vertex S is connected to a vertex T in this graph if the symmetric difference of S and T is an element of the hypergraph. Okay, that's it. That's the definition. So now what I'm going to do, because I gave you a definition and you need time to think about it, I'll filibuster for a little bit. I just like making some random comments so that you have time to think about it. Okay, so here's one random comment. I'm actually going to invoke this graph for L, which is very large. At some point, I'll invoke in the proof L, which is like n to the epsilon. So in some sense, even though my hypergraph is polynomial size, I'm actually going to think of the Kikuchi graphs even on like 2 to the n to the epsilon vertices. Okay. Another comment. This graph is in some sense very sparse. It has n choose L vertices, but an edge appears only for those pairs that symmetric difference out to a set of size 4, in particular a 4 tuple in the hypergraph. Any such edge, therefore, corresponds to a pair of sets that intersect in all but 2 vertices. So they're like sets of size L, but they intersect in a set of size L minus 2. So in some sense, there are very small number of connections, and that's going to be okay. It's a sparse graph. I'm going to work with. Good. Any other questions so far about this graph? All make sense? Actually, maybe I'll make one more filibustering comment. So if if you think of the hypergraph as giving you think of defining the Cayley graph for those in the know based on the hypergraph you have on the whole hypercube. So think of the elements of the hypergraph as generators on the hypercube. Then this graph is simply the level set of it when I take only the vertices of that correspond to having weight L vectors. If this comment was not understandable, it's not relevant for the rest of the talk. I'm just trying to like spend 30 seconds so that you can understand the definition. Good. All right. That's all. All right. So now what about it? So the key property is, and it's also all going to be simple. So the key idea is that somehow cycles in this Kikuchi graph are related to the cycles in the hypergraph that we care about. And so the eventual idea is that hopefully the cycles in this graph would be easy to reason about because graph cycles are easy objects. And therefore we'll be able to prove something about hypergraphs too. So let's try to relate how cycles in the Kikuchi graph relate to the cycles in the original hypergraph. Okay. So instead of cycles, I'll first of all look at closed walks. So closed walks are basically cycles where you can repeat vertices. So you start from a vertex, you return back to it, except that I'm not stopping you from revisiting a vertex if you would like. Okay. This is just convenient, because of the things I'm going to do later. So instead of cycles, let's consider what happens to closed walks on the Kikuchi graph. Okay. So here is the claim that I'll fill up completely when I actually prove it to you. It's a weird way of doing math, but that's what I'm going to do today. I want to claim that if I look at a closed walk on the Kikuchi graph, then in fact, there is a correspondence between such a walk and a cycle in the hypergraph I care about, or something else happens. And we'll see what that or is in a bit. So if you think about a walk, what does a walk look like? You start from some vertex at S1, then you go to S2, then you go to S3 and so on, and then you return back to S1, right? Each such transition from Si to Si plus 1, the transition happens because the symmetric difference of Si and Si plus 1 was some element of the hypergraph. Let's call that C sub I. So, corresponding to every edge that you are taking in this, in this walk, there is an element of the original hypergraph. The claim is that these elements that you're using must form a cycle in the hypergraph or something else happens. Okay. So now I'll try to prove it and then we'll see what the something else is. Okay. The proof is very, very simple. I'm going to write down, some conditions that follow immediately by just observing that, C1 is the symmetric difference of S1 and S2 and C2 is the symmetric difference of S2 and S3 and so on. So, to read this notation, think of S1 as the 0, 1 indicator vector in n dimensions of the set S1. Okay. Then notice that symmetric difference of S1, S2 is simply the addition mod 2 of the corresponding, indicator vectors in 0, 1, 0, 1 to the n. So the fact that C1 is the symmetric difference of S1, S2 means that S1 plus S2 must be C1. Similarly, S2 plus S3 must be C2, and so on. So if I add all the equations on the left side, modulo 2, then because every set appears exactly twice, I should get basically a 0 mod 2. Which must mean that the addition of the indicator vectors of C1, C2, etc. mod 2 must also be 0 mod 2. But what does addition of these vectors being 0 mod 2 mean? It must mean that every vertex appears in an even number of CIs. But that was exactly our definition of cycles. So we've concluded that C1 through CR is a cycle, except something's up. Exactly. It could be a trivial one because, so far there is no condition that forces that C1 through CR be distinct. So for example, one way that this equality could hold true is if, C1 appears twice and C2 appears twice and C3 appears twice and so on. Then it doesn't give me any cycle in the hypergraph, but of course this equality holds. Now notice that, you could say, well, suppose the walk on the Kikuchi graph is a simple cycle. Maybe this problem will be eliminated. Not true, because even though you are using distinct edges of the Kikuchi graph, each C of the original hypergraph corresponds to many, many edges in the Kikuchi graph. So even though you might be taking a simple cycle, it could still be trivial. Okay. So let's define everything else as, I'm going to use the word even returning. Okay. That's just a nomenclature. I'm going to call every set of CIs that are not hypercycles, okay, not cycles in the hypergraph, as even returning. Okay. So we now have actually a statement. Okay, so that's even returning hypercycles is a multiset of hyperedges so that every hyperedge appears an even number of times. It's in some sense the only situation that I don't recover a cycle in the hypergraph from such a walk. And I can now fill in, the whole claim. Any closed walk in the Kikuchi graph corresponds to either a cycle or must be even returning. Okay, does it make sense? Very good. All right. So now, what do I need to prove? Well, I need to prove that, a hypergraph with a certain density has a cycle of some length. A natural strategy would be to somehow construct some Kikuchi graph and try to find a cycle in this Kikuchi graph which is not even returning. Right? If I could somehow find a cycle that is not even returning, I'm kind of done of appropriate length. So here is how I'm going to accomplish this plan. I'm going to prove the following claim. I'm going to prove to you, I'll count two things. Okay, I'll fix the Kikuchi graph, and I count the number of even returning walks of a given length. Let's say the length I'm interested in is exactly 2r, so I'm going to count the number of all even returning walks of length 2r in the graph, and I'll prove to you that the number of all closed walks of length 2r is strictly larger. If it's true, then there must be at least one walk which is not even returning. Such a walk must contain inside of it a cycle that is smaller or equal to 2r in length. Everything okay? Okay, good. All right, so that's my proof plan. Okay, and actually the way I'm going to do this is by relating both these counts to spectral norms of some matrices. Okay, so I'm going to do this combinatorial counting problem by relating these counts to spectral norms of some matrices that I'm going to build out of the Kikuchi graph. Okay, feel free to stop me if there are any questions, by the way. Okay, so let's do the first thing. It's actually easy. I want to relate the number of all walks of length 2r in the Kikuchi graph to a certain spectral norm. Okay, and in fact, the matrix would simply be the adjacency matrix of the Kikuchi graph itself. So that's the 0, 1 adjacency matrix. Okay, and this proof is actually very easy. Let's see. So, the only observation required is that if I want to count all the 2R length walks, then I think this is a theorem that at least we plan to teach in undergrad algorithms classes. I don't know if it's in Bob's class, but I hope that you've seen it. If it's not, it actually has a very easy proof. That the number of 2R length walks in any graph is in fact the trace of the 2R's power of the adjacency matrix. So there's nothing special about the Kikuchi graph here. This is just true for all graphs. I'm just applying it to the Kikuchi graph. Okay, and the proof is very simple. You can just literally expand the trace of k to the 2R, as a sum over walks, and only the terms that contribute are the only ones where all of the entries of this k matrix happen to be 1. So all of these need to be edges. Okay. Anyway, so that's very good. But why does that relate to spectral norms? That's actually also a very elementary relationship. If you have an adjacency matrix, it's a symmetric matrix. It's an undirected graph here, so it's a symmetric matrix. If you take powers of a symmetric matrix, the eigenvalues of such matrices basically are powers of the original matrix. So the eigenvalues of k were like lambda 1 up to lambda n, then eigenvalues of k to the 2R are lambda 1 to the 2R, lambda 2 to the 2R, and so on. Okay. So in particular, if I took the largest eigenvalue, that's sigma max of k here, and raise it to the 2R's power, then that's clearly a lower bound on trace of k to the 2R. Right? Because trace of k to the 2R is in fact the sum of the 2R powers of all eigenvalues. So the largest one in fact must be a lower bound. Right? So in order to, the count I care about is trace of k to the 2R. That's lower bounded by sigma max of k to the 2R. So all I need to do is like prove a lower bound on sigma max of k in order to get a lower bound on the number of 2R length walks. Okay. And that's actually very easy. I'm simply going to take, if I have to prove a lower bound on, the largest eigenvalue of any matrix, I just have to exhibit one quadratic form which is large. And the quadratic form I'm using is actually trivial. I'm simply saying, take the appropriately scaled version of the all ones vector. Okay. So this is the glorified way of saying that, just take the count of the total number of edges in the Kikuchi graph and raise it to the 2R's power. After appropriate scaling, it's going to give me a lower bound on the total number of 2R length walks in the graph. Does it make sense? Very good. Let's do the other thing. Okay. Now I want to relate the length, the number of even returning walks of 2R length also to a spectral norm. Okay. So this time I have to construct a new matrix, and the way I'm going to do it is by constructing a new matrix whose entries are signings of the Kikuchi graph. What does a signing mean? I'm going to replace every one in the adjacency matrix by a plus minus 1. Okay, so I'm going to sign the edges. So the zeros stay zeros, but whenever there was an edge, I'm actually going to replace it by a plus or minus 1. Okay, and the way I choose this signing, there's going to be some randomness in it. Okay. Now you say, okay, the whole problem is deterministic. Where is randomness coming from? That's just for the sake of the proof. Okay, there's nothing random about the problem. Just that the count I care about is going to be related to the random signing. Okay, so here is the way I'm going to construct the signing. I'm going to choose an independent random plus minus 1 random variable for every hyperedge C of the hypergraph. So I have 1 bit of randomness each for each element of the hypergraph, and whenever in the Kikuchi graph there is an edge corresponding to C, I replace that entry by the sign I sample. Okay, so the same random bit appears in many places. So it's not like a it's not a matrix where all the non-zero entries are independent, but there is some amount of randomness in it. Okay, and the key claim is that the number of even returning walks is actually exactly equal to the expectation. I can take expectations because my signings are random. Expectation of trace of a to the 2R. So basically, this is a theorem of the same kind like we saw on the previous slide, except I replaced k to the 2R by this randomly signed version, and I'm now taking expectations. Okay, and the proof is actually very simple. We do the exact same expansion as before. We write down trace of a to the 2R as a sum over all possible closed walks, and I know that it's for each walk I'm going to multiply out the entries of the matrix A. But now I get to take expectation because there is randomness in my matrix. And the key point is if any B sub C, the sign I sampled, appears an odd number of times, if I use the same C in an odd number of edges, then the expectation of B sub C basically will be 0. So the only way that a given S1 through S2R walk contributes a non-zero value to this sum is if every B sub C is squared, meaning every C contributes to an even number of hyper edges inside this closed walk. But that was exactly our definition of even returning walks. So we've shown that only the even returning walks will contribute to this count. Any questions about this? Good. So that's it. That's basically it. So that's all the proof there is. Okay. And we basically can relate the trace of a to the 2r to the spectral norm of a, also pretty much the same way we were doing earlier. We used it to obtain a lower bound in the previous version of the proof, like the upper bound. Like when we were looking at all possible 2r length walks, we were getting only a lower bound. This time I need an upper bound because I'm doing the opposite side. So I need to upper bound trace of a to the 2r by some function of eigenvalues, or the largest eigenvalue of a. And actually I'm going to use some simple idea. I know the trace of a to the 2r is in fact the sum of the 2rth powers of the eigenvalues of a. I can upper bound this sum of the 2rth powers by just taking the largest one and multiplying it by capital N, the number of eigenvalues. Okay. So I basically get this upper bound that the number of 2r length even returning walks is at most, the largest eigenvalue of a raised to the 2r times capital N, the size of the matrix. All good? So we've managed to basically, reduce both these counts to, simply understanding the spectral norms of two related matrices. Okay. And really the non-trivial calculation is what, if at all, is the spectral norm of this randomly signed version of the Kikuchi matrix. If we could prove an upper bound on it that is strong enough, then we'll basically be done. Yeah. So, before I go ahead and tell you more about this, let me tell you why you might expect this to work out in your favor to begin. So, there is this old theorem of Bilou and Linial. In fact, it has gone through more updates since then. And this was part of a program to construct explicit constructions of expander graphs for those in the know. But, or Ramanujan graphs, in fact. And they proved the following theorem, which is actually interesting on its own. They proved that if A is any d-regular graph, any graph, where every vertex has degree d, then if you take the random signing of it, meaning you replace every edge by an independent plus minus one random variable, then the spectral norm of the resulting sign matrix is actually up to some polylog factors in the degree, basically root of d. Okay. Why is this relevant? Well, because if you compute the quadratic form on correctly scaled all ones vector, like we care about in our context for the Kikuchi graph, then it actually corresponds to the degree d, which means that in this case, for the case of graphs, we are actually able to prove this theorem. Okay. And so the way you should think about it is that, in principle, you can expect these kind of random signings to lead to a drop in the spectral norm from the unsigned version. Of course, in our situation, the issue is that there are much fewer random bits. So if you think about it, in this signing of this graph, there are n times d over 2 edges. And for each edge, I picked a uniformly random plus minus one random variable, which means that the amount of randomness I have is way more than n. And in some sense, the number of eigenvectors I'm dealing with, it's like an n-dimensional space. So they're in some sense, I need to union bound over 2 to the n things if all goes right. So in some sense, I have enough randomness to try to do a union bound. Of course, that's not how the proofs work, but that's for intuition's sake. In our case, in some sense, the number of the number of random bits is restricted to the number of hyper edges in the hypergraph, which is at most n square. While the size of the graph is going to be much larger. In fact, like I told you, the L we are going to invoke this theorem in is n to the epsilon, for example. So we would have very few random bits, and we still want the kind of drop in the spectral norm that, for example, Bilou and Linial observed for random signings of d-regular graphs. Okay. So that's actually all I'm going to show you for now. What I've done for you is reduce the issue of proving hypergraph more bound to basically understanding the spectral norm of signed Kikuchi matrices. I'm actually not going to give you the argument for this part right now. I'm actually going to give you a second application of the same bound before telling you a little bit about how to prove this. Any questions so far? So, we've reduced proving the hypergraph Moore bound to, proving an upper bound on this signed Kikuchi graph spectral norm. I'm actually going to give you a new application of the same upper bound. So, I'll try to motivate doing this a little bit more. Okay. By the way, when do I end? Okay, I'll end at 1. Well, I guess a little bit. Yeah, I'll see. Yeah, I'll end by 1:15 for sure. Yeah. Okay. So let me tell you a little bit about how the same object actually can lead to some algorithmic applications. Okay. So let me tell you the algorithmic problem that I'm going to be interested in now. Let's say you're given an instance of the k-sat problem. So you're given a k-sat formula, and let's say it has m clauses and n variables. Okay. Suppose your goal is to output a value v, okay, such that v is a correct upper bound on the maximum fraction of constraints that any assignment could satisfy in the formula phi. Okay. If I ask you this problem, it's very easy to solve, right? What would you do? If I give you a phi, what would you do? Yeah, v equals 1 is a perfectly good solution. So, I'm going to say that the algorithm is successful. So, if v equals 1, the algorithm is not going to be successful. But I'm going to say that the algorithm succeeds in weakly refuting the formula if the value v you output is strictly less than 1. Because in that case, such an algorithm has proven to you that the input formula phi is unsatisfiable. More generally, instead of just weak refutation, I could care about strong refutation. What that means is that I want to rule out an assignment that actually could, satisfy, let's say more than 99% of the clauses. So instead of just proving that, every assignment must miss at least one clause, I want to actually prove that every assignment must, violate a constant fraction of clauses. Okay. So now, of course, you can't expect to solve the refutation problem for unsat formulas, but in fact, you can't expect to solve the refutation problem for all formulas because some of them are satisfiable. You can't even hope to solve them for all unsat formulas because in that sense, it is basically equivalent to checking satisfiability, which we all know is NP-hard. So the question is can you give algorithms that work for the largest possible family of phi as possible? Largest possible family of phi, which are actually truly unsatisfiable, can you actually give such algorithms? Does the question make sense? So you should think of it as like the natural search analog of the question of checking satisfiability, but you are trying to ask a question that is a version of this for unsatisfiable formulas. Okay, good. So let me tell you what we know about this problem. Just like summarize the knowledge for you. Now, this is a pretty famous problem, so there's a lot of work on it. So the way I'll do it, I'll try to draw a diagram that helps you understand what we know about it. Okay. So the way this diagram is going to work, on the x-axis, I have the number of constraints in the formula, and on the y-axis, I have the running time, and both of them are written down in log scale, meaning I'm writing down both the number of constraints and the running time by taking log of the number to the base n, because I'm only plotting the exponent of n in the running time and the exponent of n in the number of constraints. Why am I doing this? Well, because as the number of constraints increase, you should expect the task of refuting the formula to get easier. If you add more and more constraints, it should only make it easier in principle to find a violation that makes it impossible to satisfy the formula. So in principle, you should expect that the problem gets easier. Of course, that's in principle. It turns out that basically complexity-wise, the problem remains basically exponentially hard as far as we know until you have at least n to the k-1 constraints. Once you have a little bit more than n to the k-1 constraints, remember n to the k is the absolute maximum you can have here. So once you have more than n to the k-1 constraints, there starts arising a sub-exponential time algorithm, and that that yellow line is not an artist's rendition; it's actually a straight line. That's the reason I'm drawing it in log scale. There is really a linear interpolation in log scale between the running time of the best algorithm we know and the number of constraints as they increase from n to the k minus 1 to n to the k. Okay. And then at n to the k and beyond, there is a polynomial time algorithm. This is the classical Aurora-Karpinski algorithm. And the point is that this curve is basically tight if you assume, for example, the exponential time hypothesis that simply says that 3-sat is going to require a fully exponential time to solve. Okay, so that's the worst case picture. Now here is the and the only thing I want to remember is that there are two inflection points in the curve. One is at n to the k minus 1 and one is at n to the k. The next thing I want to tell you is what happens to the average case version of the problem. What happens to random k-sat? Like in some sense, one reason to study random k-sat is perhaps hope that these problems will turn out to be much easier than the worst case versions. So I'm going to draw the same curve, and it turns out that the this prediction that the problem will get much easier is in fact true. It turns out that basically the same curve holds except it's leftward shifted. The first transition, the transition where there is a sub-exponential time algorithm that does better, like you can beat brute force, happens in fact right at n now. So as long as you have, let's say, n to the 1.1 constraints, you actually have a non-trivial sub-exponential time algorithm that actually can refute a k-sat formula when it is random. And there is a polynomial time algorithm at just n to the k over 2 instead of n to the k. So the curve has, like, in some sense, leftward shifted. Things have become a little bit easier. Okay. And this picture, we have much weaker evidence of why it might be tight. We have like lower bounds and discrete models. But as far as we know, this is basically the picture of best known algorithms at the very least. Good. So, and because this threshold is achieved by some spectral algorithm, an algorithm that computes eigenvalues of some matrices, people call it the spectral threshold of. Okay. Good. So, if I were to like try to write down an algebraic expression for what's happening in this yellow curve, actually this is the result. So if I parameterize the space between n and n to the k over 2 by a parameter L, then it turns out that you see that if you have n times n over L to the k over 2 minus 1 constraints, then there is an n to the L time algorithm. And now this expression should actually strike familiar to you, because it's the same kind of expression that appeared when you were trying to write down Feige's conjecture. And that's not an accident. It's in fact the exact same expression, exact same trade-off. And in some sense, one thing we are going to do is prove basically why this is happening. So in fact, both the curves are happening for the exact same reason. It turns out that the sub-exponential time algorithms are going to exist precisely for the same reason that the cycles exist at the threshold. All right, so one more very interesting phenomenon that seems to have no analog of for any of the problem that I know of is this result of Feige, Kim, and Ofek. They showed that there is a regime below this n to the k over 2 threshold, in fact polynomially below, where there are polynomial size certificates of unsatisfiability, even though we actually cannot find them, or we don't know how to find them efficiently. So for example, for 3-sat, if you give me n to the 1.4 clause random 3-sat formula, it turns out that I can actually find a polynomial time certificate, which if I give to you, you'll be able to confirm that the formula is unsatisfiable. We don't know any algorithms to find it, but there's some weird phenomenon where the certificates are existing, but even though we don't know how how to find them efficiently. And there is no analog of this phenomenon that I know for any other problem. Okay. So anyway, so basically like there's very interesting behavior in the random case, not that much interesting behavior in the worst case. So you might ask, what's actually going on? Are we somehow discovering quirks of the specific random model we are working with, or are we somehow discovering some truth that generically holds for k-sat? Like in some sense, you might expect that the worst case complexity of k-sat comes from a pathology. If it does, then you should expect this kind of a random behavior, or at least something close to it, to extend far beyond the specific random model. So you could ask, like, which is the right picture in some sense? And to basically understand such questions, Feige in 2007 introduced the smooth model. Okay, it's like a hybrid model between worst case and average case. And it's a very simple model. Here's how it works. You start from a worst case k-sat formula. Okay, and now here's what you do. For every clause and every literal, so every negation or the literal pattern that appears, you randomly perturb it. You flip it with like some small constant probability. Okay, and the formula you get as a result, I'm going to call a smooth formula. That's it. Okay, so now this random flipping actually creates enough perturbations that the formula basically becomes unsatisfiable with high probability. So you can ask the question of finding a refutation. And the question is like, is this kind of formula, are these kind of formulas as easy as random, or are they as hard as worst case? Does the question make sense? One thing you notice is that only the clause structure in this new instance is somehow, the clause structure in this new instance is in fact completely worst case, because there was nothing random about it. The only randomness is coming from like this perturbation of literals. Okay, so this is basically the result that follows also by the same kind of analysis. In fact, if you prove the spectral bound of the Kikuchi matrices, even this result falls out. And this curve should look exactly the same as I showed you for random, because the result simply says that everything that was true for random actually extends to the smooth formulas. So once you have n to the k over 2 constraint, there's a polynomial time algorithm. Once you have little bit more than n constraints, you have a sub-exponential time algorithm, and so on. Okay. Now, a little bit about the history of this result. For random k-sat, I showed you, that this theorem was already known. That was in fact what I told you earlier. For the special case of smooth 3-sat, the paper that introduced this model, Feige, was able to in fact get the green end of this curve if you care about weak refutation instead of strong refutation. But the issue was that in some sense, like in this semi-random setting, the techniques we knew were very different. So, the kind of ideas Feige had did not extend to, for example, even 4-sat. And even for 3-sat, they did not extend to strong refutation. And so what we are really doing here is basically showing that the exact same behavior holds, not just for the green curve, but also for the yellow part of the curve, for all CSPs and at the same threshold as random. Yeah, no problem. Yes, excellent question. Exact same thing. So even the existence result actually extends as is. There is a, just for example, k equals 3. If you have a smooth formula with n to the 1.4 clauses, it turns out that there is going to be a polynomial size witness that proves to you that the formula is unsatisfiable. Excellent question. We don't know any efficient algorithm to find it. In fact, yeah, not even randomized. Yeah, in fact, we have lower bounds on various algorithms that show that maybe those kind of algorithms cannot find it, as far as we know. So I think one motivation is to understand, in some sense, if you think about a k-sat instance, there are like two elements that you're picking. You're picking a collection of k-tuples, and you're picking a collection of literal patterns. You can see like, where does the hardness of the problem come from? And in some sense, I guess this whole game is motivated by questions of whether the randomness in the clause structure is important at all in this algorithm's working. So in some sense, what you're showing is, random k-sat was supposed to be very easy. And there are like two random choices you're making, which are making the problem benign, like the k-tuples that appear in the clauses and the literal patterns. And this result basically tells you literal patterns. Basically the negation patterns in each clause, right? And basically what this result is saying is that, the k-tuples could be completely arbitrary. As long as there is some randomness in the literal patterns, the problem basically is as easy as random. Yes. No, only the sign, only the literal pattern. So basically, the k-tuples are exactly the same, and you start from the original literals, and like, let's say with 10% probability, just like, flip them, each one independently. Make sense? Yeah, actually, I can tell you more offline about the other question. The other question is also interesting, and actually we can also say something about it. That's one motivation. Yes. Is also like, in some sense, we would like this kind of heuristics that we're using for refutation to be a little bit more robust to the specific random model. And, in some sense, is at least saying that the randomness in the clause structure does not matter at all. So there is some amount of robustness in how these heuristics are going to work. Right. That, right. I would suspect that would also be easy, but yeah, I don't know. Yeah. Yeah. Okay. Yeah. Because I'm running out of time, let me just say one line that the key idea here is basically the fact that we can prove the hypergraph Moore bound. Okay, like, in some sense, the reason for why these refutations exist is actually basically related to the existence of these cycles, because the cycles are a part of this witness. Okay, and the other thing I should say is that the yellow line here arises for the exact same reason that the proof of hypergraph Moore bound works, which is the spectral analysis, the Kikuchi, the signed Kikuchi matrix. Okay, so given that it's 120, I'm not going to tell you at all about the method. Okay, I'm actually, yeah, sorry to disappoint you. I had a 1.5 hour talk version of this. Sorry about that. Let me tell you the main takeaway, that basically in general, when you're trying to attack hypergraph problems, there are lots of previous efforts to try to reduce them to graph problems, but these often happen to be lossy, because it's usually not easy to capture the hypergraph kind of structure via graphs. In this kind of problems, we are getting lucky that there is somehow what appears to be a non-lossy reduction from hypergraph problem to a graph problem that we are able to somehow easily solve. Okay. Yeah, so like these three are the applications that we came up with. I showed you like maybe one more that came up last week. The hope is that perhaps there are more applications out there that you could find. Let me just end with some open questions, because lots of people who could solve them in the audience. So I just one last log, that's the nasty log that we haven't been able to remove. We've been trying to make some efforts with Benny Sudako and his students, trying to see if like we can come up with some newer ideas here, but so far I guess we still don't know what to do. This is a direction that I am really excited about. So so far as we know, if you think of like the question of taking a random 3-sat formula with little o of n to the 1.5 constraints, then we don't know any polynomial time algorithm to find witnesses of unsatisfiability for such formulas. We know they exist, as Bob was pointing out earlier. Like we know in fact that they exist even in semi-random instances. They certainly exist in random instances. The question is, can we find them? Now, people have proven lots of lower bounds for specialized algorithms for finding such witnesses. But the question is like, can you actually expect to find them in polynomial time? And there is no real reason to expect that this is hard. As in like, we don't really have any worst case hardness barrier here. It's only the fact that we have failed for a while. Yes, exactly. Exactly. That's exactly the question I was going to ask. So, in some sense, that problem was also already clear to Uri, like in 2007. He already was asking like, can you hope to find these kind of cycles in hypergraphs efficiently? The reason I feel like we might have a new attack is because in some sense, we, now have a graph problem that it's somehow related to. And the graph itself, okay, the graph itself is huge, it's exponential size, but it does have a efficient implicit description. So the hope is, or the question is, can you somehow use this new bit of information we know about these cycles to potentially help an algorithm? Yeah, of course, this is a question that Uri has been asking for a while, and I'm just going to repeat it. Can you show this weird result that, at n to the 1.4 and larger number of clauses for random 3-sat formulas, there is a witness of there is a polysize witness of refutation? Could you show it exists below that? Again, there is nothing, as far as we know, there is nothing very majorly kosher about n to the 1.4 as a threshold. We just don't know how to beat it. We have no reason to believe it is somehow optimal or whatever. We just know that it's a barrier for the kind of techniques we have. And, it's a great question to think about. And finally, this is the question I guess I began the talk with and I'll end with. Can you do this Kikuchi matrix trick for more combinatorics problems? I feel like this is likely more doable. So yeah, I'll end there. Yeah. Yeah. So, let me maybe say one easy thing, which is like very easy to do. So it might actually tell you something interesting. So let's say, you start from a random 4-uniform hypergraph. So in some sense, random is like the most benign object in the settings. That's why you want to start with it. Let's say you build this Kikuchi matrix. Then the key observation is that this Kikuchi matrix, the signed Kikuchi matrix, is in fact a sum of some, in fact, is a sum of some random matrices. And now you can just like apply a matrix Chernoff inequality black box and get the same result as below linear. So you're going to lose an extra log factor, which would have been a big bother for below lineal because they were trying to get it right for constant degrees. But if you don't care about log factors, it's completely black box. The reason it becomes a bit hairy, even for 4 XOR, is that when the graph is not random, the spectral norm is actually truly not small. So what you need to do is like take the hypergraph and decompose into pieces which are somehow have like some regularity properties, so that the resulting matrices have enough some smooth structure that makes their spectral norm small. But there also you can basically just use off-the-shelf matrix concentration. And for like odd arity things, you need to work a little bit more hard. So you need to do some hypergraph regularity decomposition or whatever that splits the graph into like better pieces, for which you can. But at the end, the tool we are going to use is simply just off-the-shelf matrix concentration. We never need to do much more. Now, to relate this off-the-shelf matrix concentration inequalities to the hypergraph Moore bound, we do have to do some trace moment calculation kind of things, but those are not essential. If you're happy with this log to the 2k kind of losses, you can do a very completely black box proof with matrix concentration. For the single log loss, by the way, we did have to be a bit more careful and use trace moment method to calculate the spectral norm of these matrices. But yeah, that's just because we were very careful about the polylog factor losses. Does that help? Okay. Any other questions?